Good morning, good afternoon, and good evening. Thank you everybody for joining us. I'm Haley Thomas with John M. Campbell & Company, and I'll be your moderator today. Today's presentation, entitled How to Squeeze More Life from Your Molecular Sieve Dehydrator, will be presented by Mr. Harvey Molino. Harvey is an instructor and consultant for John M. Campbell & Company and has over 35 years experience in the chemical and hydrocarbon processing industries, and has been associated with Campbell for over 10 years. He was heavily involved in the design, startup, and operation of molecular sieve units during his years with Union Carbide UOP. We appreciate you being here today, Harvey. The floor is now yours.
Thanks, Haley. Let's not waste any time and just jump right into the presentation. What we show on the screen is an outline of what this discussion will cover. We're going to summarize very quickly a complete adsorption cycle, and what we plan to do is take you through a 3-bed dehydrator to show you the flow of the gas during adsorption as well as what happens during regeneration. We're going to explore the transient nature of adsorption. We're going to see that adsorption is anything but steady state. We then discuss some common misperceptions in the industry about cycle times and pressure drops that could be of help to you when you evaluate your own systems that you have in your facility. We'll explore typical operating problems that have occurred throughout the 50 or so years that molecular sieves have been used in commercial services, and then describe methods to extend the life of a molecular sieve unit. Let's take a quick look at what an adsorption cycle looks like just for a review. So this is a schematic of the 3-bed adsorption system. And what we see is that 2 beds, adsorber A and adsorber B, are undergoing parallel adsorption, while adsorber C is undergoing its regeneration cycle. We show a cycle chart at the bottom which allows you to see what is going on in each adsorber. Let's take a look at the cycle chart and we'll look at adsorber A. Adsorber A goes through 2 distinct adsorption step times, adsorption 1 and adsorption 2. After the total adsorption time for vessel A is A1 plus A2. A1 and A2 are referred to as step times. So if the step time was 8 hours, then vessel A would be seeing half of the feed flow for 8 hours, and then see the second half of feed flow for another 8 hours, for a total of 16 hours of adsorption. And then vessel A, would then have to complete its regeneration cycle in the same step time of 8 hours. So just a quick review. We are adsorbing through vessel A and B in the downflow direction. And in this schematic, we are regenerating vessel C in the upflow direction, and the spent regeneration gas goes to a cooler and then to a knockout. 2 key things to take away from this. The first is that your total regeneration cycle must be completed before water breaks through during the adsorption stroke. This is a must. If this does not happen, you will have to either reduce your feed flow rate or change out the molecular sieves. A corollary to this is that your regeneration time must be less than or equal to your step time. The next thing we should look at is what happens on a bed of molecular sieve. What we show are compounds and their kinetic diameters in angstroms. The kinetic diameter is roughly the smallest diameter that a compound will have. Compounds are not spherical. They often look like sausages. So we're interested in the smallest diameter, and we'll refer to that as the kinetic diameter. When we use molecular sieves have very precise pore openings. For a molecule to be adsorbed on a molecular sieve, it must be smaller than the opening into its pores. In a type 4A molecular sieve, any molecule smaller than 4 angstroms can enter the pores. Type 4A sieves are used in most dehydrators, so components smaller than 4A will be adsorbed. In addition, if the molecule fits into the pores, if it's strongly polar, it will be held onto the surface of the molecular sieve much stronger than any nonpolar molecules. One other point to remember is that the higher the partial pressure, the more strongly the molecule is held up to a point. So we can see, if you have a type 4A molecular sieve, that anything less than 4 angstroms will be admitted to in the pores of the molecular sieve. That means carbon dioxide, water, ammonia, methane, and methanol will all go into the pores of a mole sieve, whereas propane will be excluded from a type 4A molecular sieve. This helps us explain the transient nature of adsorption. Two consequences of the transient nature could be adsorption peaks and or regeneration peaks. This occurs because there is always some amount of active molecular sieve in the bed. Let's first talk about the adsorption peaks. From the previous table, we can see that hydrogen sulfide and ethane will be admitted into a type 4A molecular sieve. Now, water is much more strongly held than H2S or ethane in the pores. So water is going to displace any H2S or ethane that may have gotten to the pores before the water. This displaced H2S or ethane results in an increase in concentration as it rolls down the adsorption bed. This increase in concentration translates to an increase in partial pressure. This, in turn, increases its adsorption capacity. So any displaced hydrogen sulfide will load up on the active material further on down the bed. And if you continue this process where the water will continue to desorb, let's say, the hydrogen sulfide, in the end, the H2S that leaves the bed during adsorption will have a higher concentration than it did when it first entered the bed. This is called a spike in the outlet concentration. It's usually not a big issue in adsorption, but you really do need to be aware of this. For example, if you're using a type 5A molecular sieve, which will admit lots of hydrocarbons into the pores, you may see a hydrocarbon spike in the outlet. This could cause issues in your downstream operations if they happen to be sensitive to hydrocarbon peaks. Regeneration spikes typically give us more headaches than adsorption spikes. Assume once again you have a type 4A molecular sieve dehydrator. If you have hydrogen sulfide in the feed, it will load up on the unused portion of the type 4A molecular sieves. During regeneration, you're going to experience a spike. This may or may not create operating issues for you. In addition to the H2S spike, you're also going to have a water spike in the spent regeneration gas. The spent regeneration gas cooler needs to be designed to handle the sudden increase in water content. The takeaway message from this simple slide is adsorption is not steady state. It is a transient process. This shows a schematic picture of what we just described with respect to components, weakly held components, loading up on the active portion of a molecular sieve bed. Here we see a molecular sieve bed with three zones that are established during the adsorption. You have the equilibrium zone, where the molecular sieve can hold as much contaminant as possible. It's reached its equilibrium. You have a mass transfer zone, where the component from the gas phase is undergoing a resistance to get into the internal pores of the molecular sieve. And you finally have a third zone, the active zone, which is waiting for the contaminant to move down through the vessel. If we took this vessel and flipped it on its side, you would end up seeing this concentration profile inside the bed. It's the water on the inlet versus the length of the vessel. And what we show is the development of a mass transfer zone. So let's take a look at partway through the adsorption cycle. Let's look at step number 4, where a stable mass transfer zone of water has been established. If we take that snapshot in time and look at this hand drawing below, this profile represents the adsorption of water. In this section of the bed, it's all active molecular sieve. What we show on here is a profile of hydrogen sulfide that has loaded on the active portion of the bed. The reason for this little increase in concentration is due to the fact that the water has displaced the hydrogen sulfide and the partial pressure has increased, so therefore the loading of hydrogen sulfide is higher in this portion of the bed because it has seen a higher partial pressure. What does this all mean? Well, what it means is, particularly during regeneration, when you are going countercurrent with a clean gas, what's going to happen is this hydrogen sulfide is going to leave the vessel faster than the water leaves the vessel. And when the hydrogen sulfide leaves, it's going to be concentrated in the regeneration gas. In a dehydrator, the amount of regeneration gas is between 5 and 10% of the feed gas flow rate. That means you're going to get a spike or a peak of hydrogen sulfide in the spent regeneration gas. Wherever the regeneration gas goes, you need to ask yourself the question of, will the downstream process be able to tolerate that peak in H2S? If you cannot, you may have to put in a small amine unit on the spent regeneration gas. In addition, you can see that the water will peak during the regeneration because we, again, are using a smaller flow rate of regeneration gas compared to the feed flow rate. So the question you also need to ask is, will the water spike throw you off specification if, for instance, you plan to blend in the spent regen gas with your with residue gas that is leaving a demethanizer? If it does throw you off spec, you may have to put in a small TEG unit in the spent regen gas line. This summarizes the schematics that we have just discussed and shows that the peaks during regeneration will end up in the spent regeneration gas, and what you'll need to do is ask yourself, where is the spent regeneration gas going, and can it tolerate the peaks? Adsorption, in addition to being a transient process, is really taking a contaminant and moving it from one stream, the feed stream, and concentrating it in the regeneration gas, in the regeneration stream. Adsorption is really nothing more than an expensive concentrator. Let's shift subjects and go into some common misperceptions that we find about adsorption times and pressure drops. One misperception is long adsorption cycles times will permit reduction of the regeneration gas flow rate. Now, this is true. If you have long adsorption cycle times, you can reduce the regeneration gas flow rate because you have more time to complete the regeneration. But there's a limit to how low you can go. If you reduce your regeneration gas flow rate too low, what will happen is that you could fall into the laminar flow region during heating. And if you fall into this region, you will not get adequate flow distribution. This will result in water leakage during your adsorption step. A rule of thumb is to keep your pressure drop per length less than 5.4 kilopascals per meter or 0.01 psi per foot. Excuse me, you want to keep your pressure drop per length greater than 5.4 kPa per meter or greater than 0.01 psi per foot. This will assure that you stay out of the laminar flow region and will give you good flow distribution. So while long adsorption cycle times will let you reduce the regeneration gas flow rate, there's a limit. You don't want to go below the recommended guidelines to make sure you stay out of the laminar flow region. The second misperception is that the maximum fresh pressure drop a bed of molecular sieve can handle is limited to 41 kPa or 6 psi. Molecular sieves can handle much higher pressure drops, probably more than a mesh and grating bed support system can withstand. The history behind these pressure drop limitations really goes back decades for recommendations posed by adsorption vendors. It represents a vendor's understanding of compression versus CapEx trade-offs. You, the facility engineer, should investigate the trade-off between high pressure drop, which translates to operating expense, and vessel diameter, which translates to capital expense. 6 pounds or 41 kPa is not a limit that is fixed in stone. Let's now talk about typical operating problems. The items listed on this slide could result in dehydrated gas not meeting specification. And you'll see that what we've done is we've put this key point here, which is that your time for completing your regeneration must be less than or equal to the step time. Let's talk about these typical problems one at a time. Liquid carryover. To avoid liquid carryover, get a good inlet filter separator. In my personal experience, over 80% of troubleshooting can be traced to a poorly performing inlet separator. A good inlet separator, a good inlet filter separator will solve the majority of your operating problems. So make sure you have a good inlet filter separator, that it is not undersized because your gas production has increased over the years. Check your low points. Sometimes low points in your feed line can collect liquids that will then be carried over into one or more vessels during adsorption. Liquid carryover can cause both a slow, steady leakage of water in the product gas and the need to change out the inventory of molecular sieve sooner than anticipated. Contaminants in the feed or in the regeneration gas are a big issue. Air dryers, for instance, can last decades because the gas is very clean. Some contaminants will cope during adsorption and increase the mass transfer zone. This can lead to a larger than anticipated reduction in the adsorption cycle. Some contaminants can react with the binder of the molecular sieve and destroy its structural integrity. Amines can do this, so can salt water. Let your sieve vendor know what contaminants are expected in the inlet gas so they can recommend the appropriate action to take. Changes in feed conditions can create issues. For instance, if you have a higher feed temperature, you're going to have more water in your feed gas, and you may not be able to complete a adsorption time before you complete regeneration. It comes back to this point over here where you must complete your regeneration cycle before a step time. And if you have more water in your feed due to changes in feed conditions, you may not be able to achieve that. The next thing we want to look at is inadequate regeneration. Not enough regeneration gas may result in the adsorption cycle finishing before the regeneration cycle. This is bad. If the regeneration flow is very low, then you may have poor flow distribution, as we discussed a little earlier. Inadequate vessel insulation can cause an excessive loss of heat near the vessel walls. Particularly in large diameter vessels, this could result in incomplete regeneration of the sieve particles in contact with the vessel wall. The result is early water breakthrough during adsorption. Poor flow distribution can result in a slow, steady leakage of low levels of water during adsorption. Make sure your regeneration pressure drop is greater than 5.4 kilopascals per meter or greater than 0.01 psi per foot. Inspect the bed supports and make sure they have room for thermal expansion, or just get rid of them and put in a good spider-type distributor and fill the bottom head with inert material. This latter approach will require more regeneration gas. A bed support failure can result in instantaneous water breakthrough. One of the things that may be obvious to some of you is that you want to have standby time built into your system during the design phase. If you can add in standby time in the initial design, you can end up buying a lot of flexibility in the operation of your system. And that brings us to extending the life of molecular sieves. Knowing what some of the typical operating problems are, the challenge is to avoid them from occurring. So be on the lookout for contributors to operating problems. You also want to run periodic breakthrough tests in the field. Maybe once a quarter or twice a year, conduct your own breakthrough tests and compare them to what you would anticipate, which we're going to show you in the next slide. And what I feel is very important is to try and build in excess regeneration capacity by way of building in standby time. By building in excess regeneration capacity during the design phase, this means that your regeneration circuit will be larger, but it gives you some margin in case you run into issues and you have to reduce the adsorption time. The only way you can reduce adsorption time is by being able to complete a regeneration cycle before the adsorption cycle finishes. And if you want to reduce your adsorption cycle time because you have, say, more water in your feed, that means you have to complete the regeneration cycle quicker. And one way to achieve that is by having standby time in the design. What we show over here is a plot of the useful capacity of the adsorbent versus the number of cycles. And we show it for good, average, and poor environments. What makes a good, average, and poor environment? Well, usually it's the contaminants that are in the gas. And the contaminants that are in the feed gas are going to be a function of the upstream operations. You have a lot of contaminants in the gas, you're going to experience a poor life cycle curve. What's common to all these curves is that they all start out with a very steep loss in capacity, and then the curves tend to flatten out. They flatten out, and as the capacity decreases, you get to a point where you will not be able to turn the beds around fast enough, and that's when you have to call your sieve vendor in order to get a fresh charge of molecular sieve. For instance, if you're at 1,500 cycles and you cannot regenerate the vessel before the water breaks through during adsorption, you have a problem. You either need to reduce the adsorption flow rate, or you need to recharge the vessels with fresh molecular sieve. If you had standby time available, what you could do is then end up regenerating the beds using that standby time, which would allow you to stay on the adsorption cycle for a longer period of time. And because these curves flatten out as the cycle increases, you can increase your life of your molecular sieves considerably by adding in standby time at the design phase. So what you need to do is periodically run breakthrough tests in the field, compare the breakthrough test to this chart, see where you are on with respect to these curves, and you will be able to predict within a fairly reasonable accuracy of when you're going to have to change out the adsorbent to fresh adsorbent. This concludes the formal presentation of this session, and we are ready now to take questions.
Ramiro from Venezuela wants to know, if methanol is present in the feed stream, how will that affect the performance and life of the molecular sieves?
Thank you, Ramiro. Well, the answer is, and particularly for you folks out there that have ever taken a Campbell facilities course, you know what the answer is. The answer is, it depends. If you are using a type 4A molecular sieve, the methanol will extend both the water equilibrium zone and the mass transfer zone. It will also load up on the unused portion of the bed. You may only be able to achieve about 1 part per million by volume or so of water in the product gas instead of a desired less than 0.1 parts per million by volume. Another issue is that methanol will decompose during regeneration temperatures higher than 232 degrees, that's 450 degrees Fahrenheit, which will slowly destroy the bed. That was 232 degrees Celsius, which is equal to 450 degrees Fahrenheit. So you need to regenerate at temperatures lower than that. If you know that methanol will be in the feed, you might consider using a type 3A molecular sieve. Methanol has a kinetic diameter of 3.76 angstroms, so it will not adsorb on type 3A. But type 3A sieve has a longer mass transfer zone compared to type 4A. This means the bed weight of type 3A will be larger compared to a type 4A for the same cycle times. So you may not be able to just switch out a 4A vessel for a 3A inventory. You will also need to reduce the regeneration temperature to 232 degrees Celsius or 450 degrees F because type 3A is not as rugged as type 4A. If you already have type 4A installed, you will need to reduce the regeneration temperature so that it does not exceed 232 degrees Celsius or 450 degrees Fahrenheit if you want to continue using the type 4A sieve. This may require longer heating times, especially if you are regenerating at higher pressure. Longer heating times translate to longer adsorption times. Can you increase the adsorption time without experiencing water breakthrough? If not, you may have to increase the regeneration gas flow rate. Can the equipment in your regeneration circuit handle an increase in flow rate? Hopefully, your system was designed with standby time, which gives you a safety margin to play with. In the extreme, you may have to reduce your feed gas flow rate.
Okay, thanks.
Next question.
All right, we have a question coming in from Heidi in Norway. She would like to know what can be done to prevent damage to the molecular sieves due to regeneration reflux.
Thank you, Heidi. Let's see. This is another case where standby time can help save the day. Regeneration reflux happens when during the heating portion of the cycle, when water condenses on the cooler vessel walls at the top of the vessel and rain downs on the adsorbent. As the heat zone moves up the bed, a rolling boil results, which can turn the molecular sieve into a powder. Repeated cycles can bake the powder into a solid cake, which drastically reduces the capacity of the adsorbent. So what do? In an operating unit, the use of ramp heating will help minimize this effect. Ramp heating means increasing the regeneration temperature in discrete steps of, say, 55 degrees Celsius, that's 100 degrees Fahrenheit for my FPS friends, per hour, until the final regeneration temperature is reached. Then what you want to do is continue regenerating for about 1 hour after the outlet temperature levels out. There are numerous variations to this recipe, but the idea is to gradually increase the heating temperature. To do this, you're going to need to increase the regeneration time, which means an increase in the adsorption time. This is why standby time can be used to help close the gap. An alternative to ramp heating is to change out the adsorbent. The reputable vendors have molecular sieves that use binder formulations that are more resistant to regeneration reflux. Before committing to a vendor, you should ask them for reference units and arrange to speak to one of their clients that have operating conditions similar to yours. Next question.
Okay, Harvey, we have another question coming in from Omar in Abu Dhabi. He would like to know, how can I minimize the H2S spike experienced during regeneration of my 4A dehydrator?
Wow. Once again, standby time can come to the rescue. The H2S peaks you are seeing may result from H2S and/or mercaptans in the feed. Both sulfur species will load on the unused portion of the adsorbent. During regeneration, the mercaptans will decompose to hydrogen sulfide and other sulfur compounds. If both hydrogen sulfide and mercaptans are in the feed, you could see two distinct H2S peaks during regeneration. To eliminate the peaks altogether, you will need to change the adsorbent to a type 3A. That's because neither mercaptans nor hydrogen sulfide can get into the internal pores of a type 3A molecular sieve. But doing so will result in the same consequences we discussed when addressing the methanol question. To reduce the peaks, you can try to increase the regeneration flow rate while ramping up the regeneration temperature. This will help smear the H2S peak out. As discussed, ramp heating requires more regeneration time, and standby time will help achieve this. If you cannot ramp heat, then increasing the regeneration flow should help reduce the H2S peak since there is more gas to dilute it with. But does your regeneration circuit have the needed excess capacity? Next question.
Ugolo in Nigeria would like to know, will compound beds of silica gel and molecular sieve minimize the damage caused by liquid carryover?
Another good question. Thank you, Ugolo. And the answer is, guess what? It depends. The best approach is to eliminate the liquids from getting into the system, and this means a properly sized inlet filter separator. As I mentioned before, in my experience, 80% of mole sieve troubleshooting can be traced to a poorly performing inlet separator. I know that wasn't the question, but having a properly sized inlet separator will prevent the majority of operating problems from occurring. So here's the deal with compound beds of silica gel and molecular sieves. It may or it may not solve the problem, and ultimately it's a function of site-specific conditions. There are water-resistant silica gels available for use in dehydrators. Silica gel has a very high equilibrium water capacity, higher than that of molecular sieves. But it is amorphous, and it is subject to coking during regeneration. What liquids are you looking at? Liquid water, liquid hydrocarbons, liquid amines, or a combination of all of these? How much liquid carryover are you looking at? The protective layer of silica gel has a very limited capacity for liquids and might be saturated very quickly. There also may be commercial issues involved. Will two different adsorption vendors be used? And if so, what kind of warranties will they offer? If you decide to use compound beds of silica gel and molecular sieves, you should ask your vendor for reference units and arrange to speak to one of their clients that have operating conditions similar to yours. Ultimately, it's a question of risk-rewards. But there is nothing better to combat liquid carryover than a properly sized inlet filter separator. Next.
All right. And Natasha in Houston would like to know, in my facility, the feed gas is heated about 5 degrees Celsius after it leaves the filter separator. Since absorption is favored at low temperatures, should we bypass the heater?
Thanks, Natasha. Are you sure you're located in Houston? Most Houston people would say 9 degrees Fahrenheit, not 5 degrees Celsius. But we'll still answer the question. Well, you know the answer to the question. It depends. You are correct that adsorption is favored at low temperatures and, by the way, high pressures. The first rule of gas processing is know where you are in the phase envelope. So, you will need to get the feed composition, plot a phase envelope, and see what it looks like and where you are operating. If you have a rich gas stream, the phase envelope will be much fatter compared to a lean gas stream. Now you might ask, what is rich? Well, this is subjective, but generally, if your feed gas has a relative density greater than 0.75 and or a methane content less than 80%, you probably have a rich gas. Perhaps a better way to define rich is to look at the natural gas liquids content. A gas with greater than 5 gallons per 1,000 standard cubic feet, which is equivalent to, let's say, 0.7 cubic meters of liquid per 1,000 standard cubic meters of gas, that is considered rich. Regardless, you need to see where you are on the phase envelope. When the gas goes through a molecular sieve unit, it will experience a pressure drop of up to 70 kPa or 10 pounds, 10 pounds per square inch. You may fall into the retrograde region of the phase envelope, which will cause liquids to condense in the adsorption vessel. This is called retrograde condensation and will be seen as a slow leakage of water in the outlet of the dried gas stream. Heating the inlet gas to about 5 degrees Celsius or 9 degrees Fahrenheit will often result in missing the phase envelope when the pressure drop occurs. Since molecular sieves love water so much, the extra 5 degrees Celsius or 9 degrees Fahrenheit should not affect the capacity of the system. Do we have time for any more questions, Haley, or how are we doing?
I think actually, Harvey, we've about ran out of time for questions. So with that being said, I want to say thank you again, Harvey, for being here with us today. Unfortunately, like I said, we didn't have enough time to get to everybody's questions, and I would like to apologize for that. Do feel free to send any additional questions to the email address on the screen, webinar@jmcampbell.com. I want to say thank you again to everybody for joining us. If you have any ideas about future webinars or any comments, please let me know at the number on the screen or at webinar@jmcampbell.com. We look forward to seeing you in an upcoming John M. Campbell & Company course. Thank you.